In this lecture, we'll be continuing our discussion about content mining in social media. First, though, to go through some announcements about course logistics. So first, for the data collection report, I'm currently working on grades for these. The intermediate report is due in a little bit less than 2 weeks, so be working on that. If you have questions for me, please reach out. Regarding your assignments, assignment 2 have all been graded. You should be able to see your grade and see the rubric with comments in Canvas. And assignment 3 was due at the beginning of this week. You still have some time to get it in. If you have any questions or concerns about this, please let me know. All right, also the ethics presentations are going on. Thank you everyone for participating in this and asking questions and answering questions from your fellow students. Note that there are 2 this week as well. But continuing on in the discussion of content mining. So from a learning objective standpoint, what is it that you want to take away from this discussion, right? So we talked last time about defining 3 content mining tasks, describing and defining sentiment analysis, defining precision and recall and F-scores for metrics, and implementing at least 1 content mining analysis pipeline. And we talked about a number of different content mining pipelines for different data types. We talked about text mining, image mining, pulling information from metadata. And last time we talked about sentiment analysis and a lot of text mining capabilities and briefly touched on some metadata analysis using or extracting timing information. So just to simply rehash, in the world of text mining, a number of things that we'll talk about include simple tokenization, sentiment analysis, topic modeling, geolocation, named entity recognition, and some other things. Last time we talked about tokenization and sentiment analysis. Specifically with tokenization, it was this idea of having a tweet or some social media message and trying to identify or extract the individual tokens or separate the individual tokens in this message from the full message itself using the natural language toolkit or whatever text analysis pipeline you want to use. But the critical aspect here is breaking up these messages or documents in some verbiage into individual tokens. And you can do this for an individual token. These are called unigrams. You can do these for pairs of tokens called bigrams, or sets of 3s, triples of tokens called trigrams. And actually, you can go up and up and up, and we talked about that. Then we spent a lot of time talking about sentiment analysis and emotion, the idea that we can take a given social media message or a given review and evaluate attitude in some way. So here, this tweet has some sort of negative attitude. Here, this tweet is relatively neutral. It's a much more objective sort of statement of fact. And here we have a tweet that has a more positive attitude. We talked about sentiment, as I said, detecting attitude. So you have some holder of sentiment who has some attitude about some target, and then we can evaluate or measure the sentiment in a message of this holder on this target. And we can project that into some scale. Maybe it's a continuous scale or an ordinal scale or a categorical scale that tells you something about positive or negative or what degree some holder has a positive or negative attitude towards a given target. Some of the examples we talked about come from movie reviews, but there are a lot of issues with this. So here are a number of different movie reviews that might be a little bit difficult for us to evaluate sentiment for. For example, that first one, I don't think that there's anything in this film that really doesn't work. So it's already, I mean, even for a human, it's kind of difficult to parse. But this person said it was a positive review. Whereas the one at the bottom, the most aggravating kind of movie that has so much potential, but unbelievably disappointing. So you would expect so much potential to say this is a potentially good movie, or that first negative review, sensational, continuous 20-minute opening take with amazing shots that tells you something good, but then it ends with this movie has little interest. This is a thwarted expectation. Ordering issues, so when somebody starts off saying something good or exhibits some positive attitude, but then swaps it at the end. And then, of course, there's always issues of sarcasm. There's not a good example here in these reviews, but sarcasm is continuously a difficult thing to study. And we talked about how you can infer sentiment or how you can measure sentiment using lexica or rules or using machine learning to try and classify or build regression models to score sentiment. With lexical sources like Vader or CentiWordNet or Luke, as being sort of the prime rule-based approaches. And then we talked briefly about supervised machine learning models that take some data set of sentiment that's been labeled, and we pre-process that data, tokenize it, featureize it, these kinds of things, and we train some supervised machine learning model that can try and recover or predict these polarity scores or sentiment scores from this data. We have a few remaining topics to discuss. So we have topic modeling, we'll talk about geolocation, image analysis, and named entity recognition, to name a few. This time, though, we'll focus only on closing the gap on these text mining kinds of tasks. So, like I said, we'll first talk about topic modeling, and then we'll talk about geolocation and NER and some other things. When discussing topic modeling, we can put forth a number of motivating questions. The first is, I have a group of people who are discussing a number of different things on social media, and I want to group them into clusters of people or communities of people who are talking about the same kind of thing. And you may imagine this is useful for doing link prediction or useful for potentially making new friends, like, oh, these people are talking about a similar kind of topic to you, so you should potentially engage with them more. So how can I group people who are talking about the same thing? If I have a given community, say I've run some community detection task on a network, I want to potentially try and summarize or get some insight into the general topics that people in a community are discussing. So then I can compare the topics discussed in one community to the topics discussed in another community. And then lastly, how are tokens in a collection of social media related? So if I have a bunch of different keywords that are all ostensibly are about the same kind of thing, so an example that we'll talk about in a minute is you can have a lot of different ways of referring to Taylor Swift or a lot of different ways of referring to the coronavirus. How do I group all of these tokens together based on some sort of consistent topic? So, for example, with Taylor Swift, you go to Twitter, you do a search for Taylor Swift, and there's a lot of kind of conversation that mentions Taylor Swift directly, talks about her music, her awards, or particular albums. If you search for the iPhone, you get information about the iPhone 12, what its specifications are, other information about Apple. If you do a search for coronavirus, you get content that includes COVID-19 and case counts, or you get content about voting. All of these sort of sets of messages are clearly related in some way. And if we look at the kind of content that's in there, so Taylor Swift, you may look for individual keywords like Taylor Swift or the hashtag or some other names that people call her like T-Swift or individual albums or song titles. If you looked for individual keywords, you could find all these messages, but maybe you don't really know all the keywords that are related to this individual topic. So how do we address this issue? And we see the same thing with the iPhone. The iPhone is in some sense a little bit easier because there's just the iPhone, but you can also differentiate between the iPhone 12 or the iPhone other models, discussions about iOS, the Pro Max, these kinds of things. All these keywords are all associated with the same general topic or idea of discussion around the iPhone. And then you have the same problem with COVID-19, especially when you have many different ways of referring to COVID-19. Do you do COVID-19 with a hash, without a hash? Do you do it with an M dash or an N dash? Or you talk about coronavirus or CD19 or SARS-CoV-2? Or if you're studying more antisocial kinds of discussion or potentially less socially desirable discussion, you may look for hashtags like Wuhan flu that are involved in this discussion, but you may not think to look for those while you're doing some sort of data collection process. So how can we group all of these keywords together? Now, one way to do this is I have a bunch of keywords that I think are related to an individual topic, right? So I know, or at least can come up with some set of keywords about Taylor Swift. I can come up with some set of keywords about coronavirus. So if I do some collection, maybe I do some random sample of tweets, or I do some random sample of Reddit posts over a given time frame, I can then look at them and sort of assign labels to them about topics. So I can manually group these messages into topics about Taylor Swift or entertainment or coronavirus or voting, all of these kinds of things. I could do that manually. But the issue is when we're talking especially about social media data, that there's just so much conversation. So there's a study from a couple years ago about something like 500 hours of content is uploaded to YouTube every hour. So clearly there's way too much information in these platforms for us to manually group all these messages or manually label messages according to their topic. Now, you definitely can do that. There's a whole area of research around content analysis that does that. But topic modeling is a little different. The whole goal with topic modeling is to provide some sort of automated method for clustering tokens into groups. Now, generally, these automated methods are unsupervised. If you look at this as a sort of a supervised task, then this becomes more of a text classification problem, which falls out of the sentiment classification task that we talked about last time. But for topic modeling, we'll specifically talk primarily about unsupervised methods for clustering. We want to take some cluster, hopefully, when we group these clusters of tokens together, that exhibit some kind of semantic relationship, that the keywords or tokens that we put into a specific group all are related to some salient idea or some common idea, and that will be the topic. That's not necessarily the case. In fact, interpreting topic models is also its own area of research. There's not a clear guarantee that this will happen correctly, or you may be confused about trying to interpret what the outcome group is. But the general goal is to group these tokens into some salient idea. Though if you don't get a clear idea out of the topics that come out of your system, that doesn't necessarily mean that you did something wrong. That is just a thing that we have to deal with. But we've seen clustering before, right? So when I'm talking about clustering tokens, we've already discussed the idea of clustering when we were talking about community detection and building graphs, right? That here, the idea of clustering is if we look for and try and identify groups of similar things, that these similar things have some real-world meaning. In the graph mining case, the similar things could be things that are in a similar community. For the text analysis case and topic modeling case, we talk about a similar having a real-world meaning. That means that these tokens are about a similar topic or about the same topic. So this actually gives us a way to do topic modeling in a very naive manner. Say we have a collection of keywords like Taylor Swift, album, music, Apple, and iPhone. And then we can create edges between these nodes based on whether they co-occur in a given message. So we've got a collection of social media messages, we've tokenized them up, these are the tokens that exist in these messages, and then we put edges between two tokens that appeared in the same message. So you can imagine Taylor and Swift appeared in the same tweet, Taylor and album appeared in the same tweet, music and album appeared in the same tweet, etc. So if we look at this sort of graphically, it appears that Taylor Swift and album are this close-knitted group, and music, while it looks like it's a little farther away, we actually see this as a 4-element clique, that all 4 of these nodes are all connected to each other. So that might tell us something about Taylor Swift, album, and music, or about discussing the same kind of thing. But if we look at the top, we see Apple and iPhone are connected. It makes sense. And music and Apple and music and iPhone are connected as well. So the iPhone was sort of a follow-on to the iPod, so there's potentially some music element there. But also Apple very heavily pushes the Apple Music service, so there's some overlap here, where people are sometimes talking about Taylor Swift and her music, but other times when they're talking about music, they're talking about the iPhone. If we apply some sort of community detection algorithm to this, then what we may find is an output like this, where music, Taylor Swift, and album are all sort of discussions about Taylor Swift, whereas the Apple and the iPhone get grouped into discussions about the iPhone. And how music gets treated is maybe a random element of the algorithm for doing tie breaking, or here in this case, maybe this music was associated with Taylor Swift and album because there are more edges going to Taylor Swift and album than there are to Apple and iPhone. But this could be a relatively simplistic way of extracting topics from a network of co-occurrences based on how you tokenized up some social media message. So that gives us a relatively naive way of identifying relationships among tokens or relationships among keywords and clustering these keywords into what you might consider to be communities, where these communities represent some idea of a topic. But you can always get more sophisticated. A popular area of research is called probabilistic topic modeling. This is a paper from David Bly, one of the earlier seminal works in this. It's called Latent Dirichlet Allocation, again a paper from David Bly from 2003. And we'll actually focus heavily on how LDA works as an example for probabilistic topic modeling. There are other methods out there, certainly methods that are better and more interpretable. We'll talk about LDA primarily because it's ubiquitous and it's relatively easy to use because there are a number of implementations available that you can very easily access. So to give you an overview of how LDA works, the idea is we have some set of documents and we want to ascribe or assign some topic or sets of topics to these documents. So that means we have some set of topics as well, topic 1, topic 2, all the way up to some arbitrary topic number k. Now generally we pre-specify k, knowing that either there is a set number of topics in the data that we're looking for, or we need to just decompose the discussion into some pre-specified set of k, because you can treat topic modeling as a dimensionality reduction task as well. And each individual topic gets defined as a probability distribution over tokens. So what this means is, if we say topic 1 is about Taylor Swift, then messages that get the topic 1 label are likely to include these tokens that have high probabilities for topic 1. So since topic 1 is about Taylor Swift, then you're much more likely to see tokens like Taylor and Swift, slightly less likely to see tokens like album and music, and very unlikely, say, to see tokens iPhone and Apple. Say topic 2 is about the iPhone, then you see the sort of opposite, where messages that get the topic 2 assignment are less likely to include keywords like Taylor and Swift, and much more likely, almost certainly, will include keywords like iPhone, and a high likelihood will include the keyword Apple. Now, you don't necessarily know what the topic means beforehand, or you may not necessarily be able to interpret the clear topics. Like here, this topic K has low likelihood of including keywords Taylor and Swift, slightly higher inclusion of keywords album and music, but also very low likelihood of iPhone and Apple. So maybe this is like general discussions about music albums, but not necessarily or explicitly not conversation about Taylor Swift. So this is what I say when we talk about probabilistic topic models. Interpreting the topic models can be a non-trivial task. As I mentioned, one of the goals in topic modeling is to be able to ascribe a set of topics or a given topic to a given document. We want to say that this document includes or is primarily about topic 1 or topic 2. Now, what this means from an LDA perspective is we treat documents not as a distribution over keywords, but as a distribution over topics. So instead of saying, well, this document is X likely to include the keyword Taylor, we can say, well, actually, this document is X likely to be about topic 1 based on the keywords that are included in it. So here, maybe our first document is mostly about the Taylor Swift discussion, has some likelihood of being about topic 2, and very low likelihood about being about any other topic. A nice value add for the LDA construct is it allows us to generate new documents. If we know what the topic distributions are, and we know what the keyword distribution or token distributions are for all of our topics, then we actually can create new content. So if we have a given tweet, or if we want to create a given tweet, what we do is we start off by drawing a distribution over topics for this document. That means what are the likelihoods that we'll see these different topics in this document. And then for every token in our document, moving down the document, we can choose some topic from this topic distribution. So for example, for the first word, we draw some topic randomly from this topic distribution for this document. And since topic 1 is the most salient topic in this document, we pull that. Now that gives us a particular token distribution, or probably distribution over tokens for that topic. And then we can randomly choose some token from that topic distribution. So here maybe we pull first either the word Taylor or the word Swift. Here we've actually, in this Taylor Swift tweet, we pulled that Taylor Swift 13. So we can randomly draw some word from topic 1's distribution to figure out what keyword there is. And we can do this for each topic, or we can do this for each keyword in our document. which gives us a way to generate new content. So LDA is called a generative model in this sense. So once we know these probability distributions, we can generate new content that is governed by these distributions. We can move down this set of tokens in the document and generate these tweets. So that's all well and good from perhaps an academic perspective, where if we know what our token distributions are for all of our different topics, and we can know what the topic distributions are in all of our documents, then great, we can generate these things. But where do we get these topic distributions for documents from? Or where do we get our distributions over tokens or keywords from for all of our different topics? So this is where the Dirichlet part of latent Dirichlet allocation comes from. So we make some assumption that this distribution of topics for a given document are what are called Dirichlet distributed. So we have some set of documents, and we have some distribution that governs all of the density of the different topics in this document based on some parameter alpha, which is a dispersion parameter that tells us, well, how concentrated are topics in documents. I'll talk about that more in a minute. And then based on this Dirichlet distribution, we can pull some topic distribution for this given document D. Now, for the question of where do the word distributions come from for our topics, it's the same process. We have some set of K topics that we've pre-specified or we know beforehand. We have a Dirichlet distribution governing the density of the different words in our corpus, or all the different words in our vocabulary for a given topic, which is this matrix of topics by keywords, right? And from that, we can pull a distribution of words for this given topic. So now we've described the processes that give us the topic distributions for our documents and the word distributions for our topics, but we still haven't figured out or explained like where this information comes from. So we've described the process, but not the parameters for these processes. So if we're constructing an LDA model, then we need to provide these parameters. So first is alpha, which tells us something about the dispersion of topics per document. That is, lower values of alpha tell us that we'll have fewer topics per document, or their topics will be more sparse. Most documents with low value, or if your alpha value is low, most documents will only cover a few topics. Now, eta is the same kind of thing, but for the relationship of words and topics, where lower values of eta indicate you'll have sparser words per topic, that most topics are constructed of relatively few words. And then finally, you have K, this number of topics. Your D is just a property of how much data you have or what data you have, but you can specify these things or change these things for a given data set. Now, again, all I've told you is what these parameters are, but I haven't really told you where do they come from. So setting these parameters really is based on what you know about the data, based on domain expertise or some analysis of the data or what your objective is. So for tweets, you would expect tweets are relatively length constrained, meaning that tweets should have fewer topics. There's just not enough room for tweets to talk about many topics. So you know something about alpha based on just that context. Lower values for, or setting values for eta is a little bit different because that's maybe more a property of the language. Maybe it's a property of the kinds of topics you're interested in, etc. Now, eta and alpha in general, you can set them as scalars, but really they have more dimensionality than that. So alpha really is a property of every individual topic. So each topic can have different values of alpha, and the eta value is a matrix of topics and keywords. So you can have topics that have different values of eta over your vocabulary. But most of the implementations of LDA allow you to specify these as scalars, in which case all of the values get the same, or all the different values in the vectors or matrices get the same value. So the objective with LDA is to infer these properties from your data set. So you want to, given some set of data and some parameters, alpha and eta, you want to take your data and infer the topic distributions for documents, and infer the word distributions per topics. This theta d and beta k, where theta is some matrix of number of documents by number of topics that tells you for a given row that's a given document, what's the distribution of topics in that document. And this beta is this k by v matrix, which is for every topic, for every row corresponding to some topic, we have a distribution over all the vocabulary words from our data set, which tells us what's the likelihood that this particular topic will emit this particular keyword. So this is what we want to pull from the data. And we can then read off the rows and columns of these matrices to get some idea of topic assignments. So for instance, for theta, we can look for a given document, or what is the most salient or highest likelihood topic in that document. Likewise, for a given keyword, we can look across the column or look down the column in beta to figure out, well, what's the most salient topic for this keyword. There are many implementations of LDA out there, like I mentioned. So GenSim is an existing Python one that has a number of different parameters and some different implementations for parallelization if you want to go faster. From an implementation standpoint, how do we set these parameters? And the nice thing is, especially in some of the prominent implementations out there, you don't really have to set these alpha and eta parameters. So if you go look at LDA or at the LDA model in GenSim, you actually see alpha and eta have default values for you, where alpha has one that has a symmetric value that says, well, we don't necessarily know what that value is, but we'll make it symmetric across all of our topic documents. And eta, we don't have a value either. We'll learn it from the data. Nicely, I mean, you need to have some idea of what these parameters mean, but when you actually apply the model, it's not necessary for you to immediately know them. You can actually explore your data set by changing values of alpha and eta and then reviewing what the topic distributions come out as. But as I mentioned, you could use domain knowledge here and make some educated guesses or constraints about what these values should be. So at least when you're dealing with tweets, alpha should be low because tweets just aren't that long, right? Now, maybe you don't necessarily know what low is, but if you're trying to run LDA on tweets and then LDA on Reddit posts or LDA on Facebook posts, what you can say pretty definitively is it's likely that these longer posts on Facebook and Reddit are likely to have higher alphas than Twitter because they lack the length constraints that Twitter has. So you can use some of your expertise or knowledge of the domain here. I mentioned you can explore your data set by changing these values of alpha and eta and changing your values of k, and that's great. You can then review the resulting distributions of topics for documents or the distributions of words for topics and sort of try and interpret them, but that doesn't necessarily tell you if your model is good. If you have some idea of interpretation, maybe that's enough, but maybe you want some metric for this. So how do we know whether a given topic model is good? Generally, this is done by measuring what's called the log likelihood, or the likelihood of your data being produced from the model that you've created. So the data is the data, you can't really change that, but you can measure, well, given this model that I've learned or inferred from this data, how likely would it be to produce the data that I've seen based on this model? But then you make some assumption that models that are more likely to produce the data that you've seen are somehow better because they somehow fit the model, or rather they fit the data more. Now we talk about this as log likelihood because likelihood values for like relatively complex documents can be very, very low probabilities. So we take the log of them to make it a number that we can manage more easily. In terms of evaluating the goodness of your topic models, is an existing area of research. So especially when we're talking about trying to interpret topic models, there's research here that has some sort of surprising results. Primarily that topic models that perform better with these high likelihood values actually may make for less meaningful topics in general. So this paper goes through some other metrics that you can use for evaluating and interpreting topic models. I encourage, if you're interested in this kind of thing, this is a good paper to read because it talks about like why we should have good interpretability for topic models, how we can generate this. But for our purposes, now you have an understanding of what LDA is and how to apply it, how to interpret its results. You can play around with this more. Now, as I said, there are other models besides LDA for doing probabilistic topic modeling, one of which is called the author topic model. So for LDA, we have these word distributions for topics, and then we have topic distributions for documents. The author topic model makes some additional assumption or builds some additional expertise or knowledge into our model, and that's namely that a single author generally discusses only a few topics. So then you have for topics, you have distributions over words. For documents, you have distributions over topics. And for authors, you also have distributions over topics. And then you can connect authors and documents and add in some additional information here that people who are, or authors who are talking primarily about tech may not be talking about marine biology topics. Or people who are talking primarily about politics may also, or are less likely to be talking about entertainment. So this gives us an additional set of information when we are trying to build our models. And the author topic model is also available in GenSim, and is a good way to, or a good starting point for social media, because we have this author idea. Now, it doesn't work in other places like Wikipedia or maybe news articles. I guess news articles have authors associated with them, whereas Wikipedia articles don't. So your decision about application of the author topic model is based more on, again, the expertise or domain knowledge. Going back to the motivating questions for topic modeling, now we can sort of address these one by one. So for questions about grouping people based on the topic, so if we go to Twitter, we go to Reddit, one of these platforms, we pull a lot of documents from this platform, or a lot of messages from this platform, then we can use LDA to identify topics in these messages. And then for each message or for each tweet here, we can go through and identify what's the most salient topic in this tweet, and we assign that tweet that topic. And then we can group all users into clusters based on, well, here's all of a given user's tweets, and each one of these tweets has an associated topic ID. So let's count up how many times this user tweets across all these topics, and then we'll group users based on similar numbers of topics. So if you've primarily only talked about topic 1, then you should be grouped with other users who also primarily talked about topic 1. So next question about what topics are people in a given community discussing. So if we want to characterize what a given community talks about, so then we take our data, construct some network like we talked about before. Maybe it's a follower network or a retweet network. And then we take all of the documents in our data set and we apply LDA to all those topics. And then look at tweets from a given community, and we can label that community based on the most tweeted topic as well. So similar to what we did with individuals, we can go through all the tweets from a given community, or all the tweets from authors who are in that community, count up the most salient topics for all those different tweets, and then we can rank, well, what's the most tweeted about topic in this community? And now we've got some characterization. And then lastly, what's the relationship among tokens in our social media data? We can actually read this from our beta matrix and say, well, the columns here tell us this relationship among tokens. So that's enough about topic modeling. I'll go briefly through these other tasks around text mining, and that'll wrap us up for today. So I'll talk about 3 different tasks or 3 different sort of content mining approaches, and the important thing is that they build on each other. The first is part of speech tagging. I'll talk briefly about what this is and define the task. And then I'll talk about named entity recognition, which relies on this part of speech tagging. And then I'll talk about geolocation, which we've already discussed to a degree, but now we can talk about other ways to do geolocation. Part of speech tagging is the process of taking some message or some sentence in a message, and for each word in that sentence, we want to identify a part of speech tag for that word. So if you have the sentence, she sells seashells on the seashore, then we would go through the tokens in that sentence and assign specific parts of speech to each one. So for example, in Twitter, you have some tweet. We're going to tokenize that up into our sets of words. We have some set of parts of speech tags, and now we want to connect the keywords to those parts of speech. So we have adverbs and nouns, verbs, propositions, or prepositions and pronouns, and we want to connect these words to tags. So what do we use this for? Why is it useful? So here, say you have these two different messages, a sweet for my sweet, and this candy tastes too sweet. From a part of speech tagging perspective, then we can actually say, well, while we see the word sweet in a number of different places in a number of different contexts here, part of speech tagging actually lets us do some amount of disambiguation. That here, this word sweet is different than its usage in this second sentence here. That a sweet for my sweet, that sweet at the end, sweet is referring to a person, so that's a noun. Whereas here in the second one, the candy tastes too sweet, then this sweet is referring to taste, and it tells us something about the candy, so it's an adjective. So if we're doing sentiment analysis, we may treat these things differently. So for example, knowing that a instance of sweet is a noun, maybe that tells us something about your disposition towards that person, but it doesn't, in that first sentence, tell you something about your thought about or your attitude towards the sweet itself. Whereas in the second sentence, if we're talking about the attitude towards the candy, well then now we know something about the attitude towards the candy. If we're looking at social media content, we want to do some analysis of reviews, and here we have this tweet about Christopher Nolan's new movie Tenet. And you may want to ask, well, are numbers or different parts of speech in this tweet really valuable for understanding sentiment? So does like the value 2020 tell us anything about whether somebody is for or against or has a positive or negative attitude towards this movie? Same thing, does the mention of Nolan or the mention of the movie itself really tell us anything about the sentiment? So by looking at this content and then breaking it down into different parts of speech, so then breaking down this tweet into its constituent parts of speech, if we're trying to do sentiment analysis, well then perhaps we only really care about adjectives and adverbs, and the nouns we can discard or the numbers we can discard. And by doing this part of speech task or part of speech tagging task on this data, we can then reduce the amount of data that we need to pay attention to, or we can tune or change how we associate or score different words based on their parts of speech. I won't go into a lot of detail about how part of speech tagging is done. I'll save that for your natural language processing course. But I will tell you that part of speech tagging can be difficult, primarily for issues around ambiguity in language. So here I've already shown you this one example about two different senses of the word sweet. We can see that here, plants need light versus she plants a tree. Again, we have different senses. The way this works for part of speech tagging is you build up what are called parse trees, and then you try and optimize your parse tree or optimize the tags that give you the highest likelihood parse tree. But there's always going to be ambiguity in language. Now, these top ones you may think are relatively clear for humans to do, but this bottom one, this ambiguity in language, is more than just, well, what sense is the word? So here, when we talk about flies like a flower, are we talking about flies as in a plural noun? Or are we talking about flies as in the verb? It's not really clear from this sentence. We'd probably have to take in additional context from other sentences around it to understand what's being said here. So part of speech tagging isn't just difficult because of ambiguity in the language in the syntax here, but also because language is itself ambiguous, and even us as humans cannot tell you definitively what the right answer is for a given sentence. And then all of this is complicated more by social media, where you have informal language that can have misspelled words, or people use here yes with many s's to denote some kind of emotion or stylistic signal that gives you a word that may not be in your dictionary for part of speech or may not be in your dictionary for sentiment. So we have to deal with these sort of noise issues as well. Now, the way we do parts of speech tagging are similar to what we do with sentiment. You can do rule-based analysis, you can do machine learning. I'm not going to go into detail here, but naturally there's a lot more recent work on using machine learning for doing part of speech tagging than any sort of rule-based approach from before. In the Natural Language Toolkit, textbook, there's a whole section on tagging words for doing part-of-speech tagging, if you want to check that out. Spacey, which is a really powerful package in Python for doing natural language processing. It also has its own part-of-speech tagger, primarily because part-of-speech tagging is sort of it's sort of like tokenization, in which many things sort of rely on having good parts of speech tags in order to do follow-on tasks. So for Spacey, the example that they include is Apple is looking at buying UK startup for $1 billion. So it goes through this text, and then you can pull out simplistic parts of speech or more sophisticated parts of speech. So building on parts of speech is this idea of named entity recognition, which is another task in content mining where we want to then look at text and try and identify names from this text. So like I said, this often relies on part-of-speech tagging because the first thing that we want to do is look for nouns, because things that are adjectives or adverbs or prepositions are not likely to be names, as you might expect. So why would we want to do this? Maybe we want to do identification of, is somebody talking about an organization or a place or a person? Clearly extracting named places gives us some idea for doing geolocation that we'll talk about in a minute, but also identifying persons and organizations are useful if you're trying to do what's called wikification. So you go through and look for these named entities in a given document, and then you look for links to those or pages that describe those named entities in your wiki. This is partially how Wikipedia works, that allow you to read through a given paragraph in Wikipedia, and it highlights or provides links to other Wikipedia pages that mention individuals or mention organizations or places. So how do we do named entity recognition? Again, you can have rule-based NERs, a lot based on sort of hand-coded rules like regular expressions, which can be relatively sophisticated pattern matching approaches. Again, I won't go into that. You can use statistical models for doing named entity recognition that rely on like Bayes' theorem or do sequence modeling. Or you can rely more recently on neural models. There's a lot of recent work in this. So this year actually there's a good paper on surveying deep learning for named entity recognition. Spacey has its own named entity recognition package, so you can go through and extract items or extract entities from your tweets, which may be useful for doing like mentioning. Then you can imagine applying some named entity recognizer to this text. So then we can extract or identify Melbourne and East Gippsland are named entities, and we can figure out, are they places or organizations or people? And if they're places, then we can geolocate this content. Now, this is useful for a number of reasons. We already talked about geolocation and graph mining, where you somehow know locations of some number of people in your graph, and then you can build your graph of, for instance, strong ties, and then use the nodes locations that you know to sort of propagate these locations to neighbors. And you can do this some number of times until you reach stability or you've gone through some number of iterations. But how do you know what these individuals' locations may be? So sometimes they may tell you. So you could look at their profiles that has some text in it that tells you where these people are, or give some self-reported thing. So for here, if we're going back to the example with wild weather is saturating Melbourne, if we go through and identify what are proper nouns in this tweet, then we can extract Melbourne and we can extract East Gippsland. So that tells us something about, all right, there are locations here, they're named entities Melbourne and East Gippsland. We've used NER to tell us that not only are there names, but they are proper names. So now let's go through and try and geolocate these places. So how do we do the geolocation? One of the standard approaches for this kind of geolocation from text is to use what are called gazetteers, which are these big databases of location names, which have been highly curated over the years. So for instance, GeoNames is one. So you can imagine taking East Gippsland and throwing it into GeoNames, and now you get a lot of information about it. So you know the country, it's in Australia, which maybe we would have guessed from Melbourne, but we also know or can identify its latitude and longitude, and we get some additional information that it's a second order administrative division and what its population is. So we can say, oh, well, East Gippsland is 40,000 people. So that tells us something about fires are threatening an area that contains about 40,000 people. As I mentioned, these gazetteers are fairly popular and robust. So the Geolocation API from Google Maps actually is a similar kind of gazetteer where you can provide the API some string, and it tries to identify where that string is in terms of a place name, and then can give you back that geolocation information, which you can then use to infer other people's locations or an individual's location. But you should be careful. So one of the ways you can view this class is by saying, here's my telling you a bunch of different tools that you can use. But I think a better sort of view of this class is, sure, there are many tools out there, but you should be careful, and here are the ways you should be careful. Now, one of which is, if you're trying to do text-based geolocation, you'll encounter these kinds of issues, where this person here said his location was Mars. If you go and assume that Mars is a valid geolocation, or a valid name of a place, if you go to a gazetteer and you put in Mars, then you end up with what is a legitimate response, that according to GeoNames, Mars is a place in France. Specifically, it's a park in Campo de Marte in Paris. Or Mars is a populated place in Russia, or it's a locality in Yemen. Now, I think what's much more likely is this person put Mars as a joke, talking about Mars the planet, but if you assume that that's a valid entry, or if you assume that all entries in this location field for Twitter are in fact valid place names, then you will end up with this issue where now you're saying this person, or maybe there are a lot of people who are in this particular park in France, when that's almost certainly not the case. So this is a thing that you need to be careful of when you are just applying these kinds of tools to what's potentially noisy social media text. Also, or what's valuable here, and what you hopefully took away from the Goldbeck paper, is that you can apply or integrate content-based mining or content analysis with graph analysis or graph mining to get some improved pipeline for whatever task you're looking for. So in this case, by looking at a network of people and what their locations are, and incorporating gazetteers or the information they're sharing about their location via the messages they're posting, we can actually do better in terms of geolocation than just doing one or the other. I'll also note from a geolocation standpoint that Twitter provides some of this geolocation in terms of metadata. So this is another opportunity for metadata mining, where if you go look at tweets that include place names, they'll give you, or you get some amount of information about what that place is, a URL for that place, and some GPS coordinates around that place. Also, people can tweet with specific GPS coordinates that are also get embedded in the metadata for a given tweet. But note that these things are not hugely common in Twitter, and actually not at all present in places like Reddit, right? So if you're doing analytics on Reddit, you won't be able to get this, or you'll have to rely on some sort of gazetteer source like OpenStreetMap or GeoNames or the Geolocation API from Google or Google Maps API. But in Twitter, you can rely on this as well. All right, so going back to the learning objectives for today. So overall, content mining has 4 learning objectives. What we've talked about today are really about 1 and 4, right? So we've talked about additional content mining tasks, part-of-speech tagging, name entity resolution, geolocation, topic modeling. All of these are different sorts of content mining tasks. And we talked a lot about how LDA works and how you might implement it or use it in a pipeline. So now you should have some additional methodology for doing content mining for topic modeling. And I've shown you some tools for doing part-of-speech tagging, named entity recognition, and geolocation, or with tools like Spacey. Now this gives you more insight into, or more flexibility in the kinds of content mining analyses that you can do for your next assignment. All right, thanks. I won't post any new discussion questions for the content mining module for today, since there are already some from last time. But if you do have any questions, feel free to post or reach out to me.